For 60 years, University Technology Mara, or UITM, has been the place for acquiring knowledge and developing capabilities. From a training center to now a vast network of universities, UITM has campuses and faculties all over Malaysia. UITM allows for the pursuing of goals and earning a degree in any field of choice, with a mission to enhance the knowledge and expertise of Bumiputras in all fields of study, through professional programs, research work and community service, while upholding moral values and professional ethics. Nestled amidst the greenery and some of the most scenic areas in the country, each university campus is strategically located in places where their presence inevitably provides an economic boost to the local community. The Vice-Chancellor is the Chief Executive Officer, heading the academic and administrative management of the university. UITM pledges to provide maximum opportunities to pursue professionally recognized programs of study in science, technology, industry, business, arts and humanities. University Technology Mara offers quality education at all levels of study, from foundation to postgraduate. The university has always been at the forefront in science and technology as well as in management. It is a place where talent, skills and excellence are nurtured. UITM has a mission to empower the indigenous people through the provision of higher education in accordance with Article 153 of the Malaysian Federal Constitution and Act 173, University Technology Mara Act 1976. Duli Yang Maha Mulia, Sri Paduka Baginda Yang di-Pertuan Agong is the Chancellor of UITM by virtue of his status as the King, as provided for by the law. UITM has established 8 centers of excellence and 1 high COE to enhance the scholastic, creative and innovative capabilities of the university, as well as to facilitate and manage research and development. To complete the teaching and learning activities at UITM, the university has made available modern and contemporary facilities such as the UITM Stadium, the house of UITM FC. With a capacity of 6,000, the stadium is the heart of soccer and it has played host to an international match in 2009. UITM also has an Olympic-sized swimming pool for the use of students and staff. The pool is also open to public on certain days. Built in 1972, Perpustakaan Tun Abdul Razak, or the PITA Library, has grown by leaps and bounds, housing thousands of international titles for all programs of study. Students' participation in extracurricular activities is highly encouraged and supported by the university. These activities would not only equip students with soft skills, but also train them to be balanced and holistic individuals to meet global requirements. As the largest public university in Malaysia, University Technology Mara has produced thousands of alumni who are successful individuals in their disciplines. They are award winners, innovators, entrepreneurs, and leaders in both the government and private sectors. UITM honors its alumni by engaging them to establish smart partnerships resulting in strategic alliances. The alumni also gives back in areas such as academic improvements, charity work, and fundraising. University Technology Mara, Usaha Takwa Mulia. For 60 years, University Technology Mara, or UITM, has been the place for acquiring knowledge and developing capabilities. From a training center to now a vast network of universities, UiTM has campuses and faculties all over Malaysia. UiTM allows for the pursuing of goals and earning a degree in any field of choice, with a mission to enhance the knowledge and expertise of Bumiputras in all fields of study, through professional programs, research work and community service, while upholding moral values and professional ethics. Nestled amidst the greenery and some of the most scenic areas in the country, each university campus is strategically located in places where their presence inevitably provides an economic boost to the local community. The Vice-Chancellor is the Chief Executive Officer, heading the academic and administrative management of the university. UiTM pledges to provide maximum opportunities to pursue professionally recognized programs of study in science, technology, industry, business, arts and humanities. University Technology Mara offers quality education at all levels of study, from foundation to postgraduate. The university has always been at the forefront in science and technology, as well as in management. It is a place where talent, skills and excellence are nurtured. UiTM has a mission to empower the indigenous people through the provision of higher education in accordance with Article 153 of the Malaysian Federal Constitution and Act 173, University Technology Mara Act 1976. Duli Yang Maha Mulia, Sri Paduka Baginda Yang di-Pertuan Agong is the Chancellor of UiTM by virtue of his status as the King, as provided for by the law.
Bismillahirrahmanirrahim. Assalamualaikum and good morning, ladies and gentlemen. My name is Dr. Nifasdin Ismail and I will be the moderator for this opening ceremony event. It is my pleasure to welcome you to the 2021 IEEE International Conference in Power Engineering Application ICPEA 2021, which is organized by Center for Electrical Power Engineering Studies, CPES, University Technology Mara, Shah Alam, Malaysia, and co-sponsored by IEEE Power and Energy Society, PES, Malaysia chapter. On behalf of the organizing committees, I would like to express a very warm welcome to the Assistant Vice-Chancellor for College of Engineering Studies, Professor Surveyor Engineer Dr. Haji Suhaimi Abdul Talib, for accepting our invitation to officiate this event. To begin our opening ceremony this morning, I would like to invite Professor Engineer Dr. Zuhaina Zakaria, Chair for ICPEA 2021, to give a welcome remarks.
Thank you, Dr. Nick. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. First of all, I would like to acknowledge the presence of our guest of honor, Professor Surveyor Engineer Dr. Suhaimi Abdul Talib, Assistant Vice-Chancellor, College of Engineering Studies, University Technology Mara, Professor Engineer Dr. Hazli Mukhlis, Chair for IEEE Power and Energy Society, Malaysia Chapter, Associate Professor Engineer Dr. Ahmad Farid Abidin, Acting Dean, Faculty of Electrical Engineering, University Technology Mara, and also our keynote speaker, Mr. John McDonald from GE Grid Solutions. Ladies and gentlemen, I'm very pleased to officially welcome all participants to 2021 IEEE International Conference in Power Engineering Application, or in short ICPEA 2021. This is the first conference organized by the Center for Electrical Power Engineering Studies, and we would like to thank IEEE Power and Energy Society Malaysia chapter who supported us as the co-organizer for the conference. The aim of this conference is to bring together researchers from universities and also industries to stimulate exchanges of research findings and also discussion on various topics in power engineering applications. The preparation for this conference has started a year ago, and initially we planned to organize this conference as a physical event. However, with the COVID-19 pandemic situation and traveling restrictions are still in place, we have to transform this event into a virtual platform. And I believe that organizing this event as a virtual event turned out to be a blessing in disguise, since we have attracted many international papers such as from Bangladesh, Cameroon, Egypt, Indonesia, Iran, Iraq, and also UAE. In fact, our keynote speakers is from one of our keynote speakers from USA, and technology has helped us possible to bring him to Malaysia virtually. Thank you, John, for being with here today, this morning. Therefore, I would like to dedicate a special acknowledgement to both speakers, Mr. John D. McDonald from GE Grid Solution and also Engineer Dr. Muhammad Fadil Muhammad Siam from Tenaga Nasional Berhad for their invaluable contributions to the success of this conference. And I hope both keynote speeches would bring much benefit to all participants. Ladies and gentlemen, on behalf of the organizing committee, I wish to extend my appreciation to our gold sponsor, Malacca Corporation Berhad, for supporting our mission and making this conference possible. And also a big thank you to all authors for your paper submission to ICPEA 2021 and to all reviewers who have helped us in the reviewing process. Finally, a special tribute to the organizing committee and individuals who have invested much time, effort, and also resources in making this conference a reality. Thank you very much again, and I wish everyone a fruitful conference. Thank you. Back to you, Dr. Nick.
Thank you, Professor Engineer Dr. Zuhaina, for the welcome remarks. Moving right along, it is my pleasure to invite Professor Engineer Dr. Hazli Mukhlis, Chair for IEEE PES Malaysia Chapter, to deliver his welcome remarks.
Thank you, Dr. Ni. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to all the audience. I am pleased to welcome you to the first IEEE International Conference in Power Engineering Application, or in short ICPE 2021. First of all, I would like to record my appreciation to our guest of honors today, Professor Severe IR Dr. Haji Suhaimi Abdul Talib, Assistant Vice Chancellor, College of Engineering Studies, and distinguished keynote speakers, Mr. John D. McDonald and I, Dr. Fadil Muhammad Siam, also the acting dean of Faculty of Engineering, APIR Dr. Ahmad Farid. Your presence today is a great honor to this conference. I would like also to wish my appreciation to ICPE 2021 committees led by Professor Dr. Zuhaina Zakaria for managing this conference very well. It is a great honor for IEEE PES Malaysia to work with Center of Electrical Power Engineering Studies, UITM Shah Alam, as a co-sponsor in organizing this conference. Indeed, this cooperation has led to a this important conference. IEEE PES Malaysia is always committed to support such activities, which is in line with IEEE PES mission to be leading provider of scientific and engineering information on electrical power and energy for the betterment of society. I hope IEEE PES Malaysia will be given an opportunity to support this conference in near future. I believe this conference will provide excellent source of great ideas of research in the area of power and energy system. This conference also provide a best platform for us to know each other and in the long run, creating an international networking among researchers from various countries in the area of power and energy system. I'm sure you will have fruitful and rewarding discussion in this 2 days conference. Finally, I would like to thank distinguished keynote speakers, presenters, participants, and committees for your valuable contribution in ICPE 2021. I hope you will enjoy this exciting conference despite it is a virtual mode. I wish to meet you again in 2022 conference, and hopefully this time it is a face-to-face conference. Thank you to all and stay safe. Thank you. Over to you, Dr. Nick.
Thank you, Professor Engineer Dr. Hazli Mukhlis, for the welcome remarks. Now, to kick off this opening ceremony events, I would like to invite Assistant Vice Chancellor for College of Engineering Studies, Professor Surveyor Engineer Dr. Haji Suhaimi Abdul Talib to convey his welcome address and subsequently officiate the ICPEA 2021.
Thank you very much, Dr. Nick. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and a good morning. Ladies and gentlemen, allow me to begin by acknowledging Professor Engineer Dr. Zohaina Zakaria, Chair of the International Conference on Power Engineering Application, in short ICPEA 2021. Professor Engineer Dr. Hazli Mukhlis, Chair of the IEEE Power Energy Society Chapter, Malaysia. Mr. John McDonald from the United States. Mr. McDonald, I'm not sure it's morning. I believe you are in the evening, so a very good evening to you. And Engineer Dr. Fadil Muhammad Siam, our two honorable distinguished guest speakers, Associate Professor Engineer Dr. Ahmad Farid Abidin, Acting Dean, Faculty of Electrical Engineering, UiTM, the ICPEA Organizing Committee, distinguished guests, ladies and gentlemen. On this auspicious event, it is my pleasure to welcome our distinguished guests as well as participants from universities and various institutions near and far to this virtual IEEE International Conference in Power Engineering Application, ICPEA 2021. Allow me to convey my warmest greetings to all keynote speakers, presenters, and participants from local and international organizations for their commitment to participate and make this international conference a success despite challenges posed by the COVID-19 pandemic. No doubt, COVID-19 has disrupted every aspect of our livelihood. However, the severity of this disruption has made us realize the importance of being resilient, flexible, and adaptable to the new norm in this challenging time. Ladies and gentlemen, today's event is a significant initiative led by the Center for Electrical Power Engineering Studies, Faculty of Electrical Engineering, UiTM, with support and sponsorship from the IEEE Power and Energy Society Malaysia chapter, bringing together researchers, academicians, students, engineers, and practitioners to bridge gaps and share latest findings, ideas, current developments, and applications related to various aspects of power engineering. This event will serve as a platform to gather and disseminate knowledge, as well as pioneering innovations for benefit of all. I foresee that this intellectual discourse will result in future collaborations between universities, research institutions, industry, both locally and internationally. Ladies and gentlemen, glancing through the topics to be addressed through this conference, I am amazed by the diversity of power and electrical engineering related fields. They range from electronics to high voltage engineering, technology, even embracing the aspect of power system economics and electricity market. Developments in the field of electrical and power engineering have progressed steadily since the Second Industrial Revolution. Throughout history, there is no doubt that the development of this area has contributed to the betterment of every aspect of our life. With Industrial Revolution 4.0 upon us, we are witnessing an integration of various industries such as big data and intelligent system that allows for higher flexibility with endless possibilities to further improve the quality of our life. Thus, there is a great need to capitalize on the advances in technology and engineering knowledge to produce even more game-changing breakthroughs. Here at the university, we remain committed to support initiatives that can bring forth impactful advancement in academic excellence and cutting-edge technology. Throughout this conference, we shall all look forward to partners in academia and the industry to actively strategize, explore, and share technological advancement. For new innovations to occur, it cannot take place in isolation, but through interdisciplinary collaboration. Looking ahead, I am confident that through all our efforts, we will be able to achieve more. Finally, I would like to congratulate the Faculty of Electrical Engineering UiTM for their tireless effort and hard work towards organizing this event. Your enthusiasm in contributing and achieving more in the field of power engineering and technology is commendable and very much appreciated. Last but not least, I wish all of you a successful, productive, and interactive virtual time ahead, and may this international conference be the beginning of many new partnerships that will flourish into a long and lasting friendship. On that note, and in the name of Almighty Allah, most beneficent, most merciful, I humbly launched the IEEE International Conference in Power Engineering Application, ICPEA 2021. Ladies and gentlemen, thank you very much for your time and attention. Assalamualaikum warahmatullahi wabarakatuh. Over to you, Dr.
Thank you, Professor Surveyor. Insinyur Dr. Haji Suhaimi Abdul Talib for the opening remarks. With that, ICPEA 2021 is officially opened, and let's watch a video montage specially compiled by the organizer. We proceed with announcement of Best Paper Awards for this conference. We have chosen 5 papers based on the scores given by the reviewers. These are the papers. Track, High Voltage Engineering and Technology, Positive Cloud to Ground Lightning observed in Shah Alam, Malaysia based on Safir 3000 Lightning Location System. Authors, Dalina Johari, Muhammad Faris Aiman, Misri Amir, Norazlan Hashim, Rahimi Bahrum, and Farah Nadia Abdul Haris. Track, Electrical Machine and Drive, Analysis of Fault-Tolerant Dual 3-Phase Induction Machine using Graphical User Interface. Authors, Wan Noraishah Wan Abdul Munib, Han Senchi, Mahdi Toizizadi, Muhammad Hazizi Ahmad Khairi. Track, Power Electronics and Applications, a new configuration of 2-dimension extensibility-based DC source and switch capacitor boost multi-level inverter with reduced components. Authors, Yu Wai Sai, Ka Hao Lo, Learning Gopal, King Han Lim, and King In Wong. Track, Renewable Energy and Storage, Solar Irradiance Prediction for Voltage Variant Analysis in the GCPV system using LSSVM. Authors, Fahtim Hamami Anwar. Track, High Voltage Engineering and Technology, Electrical Properties of Waste Mineral Oil recycled under various treatments and doping with nanoparticles for transformer applications. Authors, Muhammad Haikal Muhammad Tukiman, Nur Sabrina Suhaimi, Muhammad Faiz Maddin, Abdul Rashid Abdul Rahman, and Muhammad Ishaq. Congratulations to all winners. On behalf of organizing committees, we would like to express our big gratitude to Malakoff Technical Solutions Sediam Berhad, a subsidiary of Malakoff Corporation Berhad, for their gold sponsorship. We really appreciate your full support and participation in this conference. Now, let's watch the corporate video from Malakoff Corporation.
Teknik Janakuasa Sendirian Berhad, or TJSB, has built a solid reputation in Malaysia as well as internationally for over 20 years as one of the most reliable and high-performing operations and maintenance service provider in the power and water industry. Our story began as the O&M service provider for Sagari Energy Ventures in 1993. The largest combined cycle gas turbine power plant in Malaysia. From then, TJSB became Malaysia's sought-after provider of operation and maintenance service. TJSB's business includes operation and maintenance, maintenance repair and overhaul services, as well as technical training and competency and consultancy services for the industry. Our operated plants produce over 1.4 million cubic meters of water and generate 7,500 megawatts of power every day. The flagship of our operated thermal plant in Malaysia is the Tanjung Bin Power Plant in Johor, which is capable of generating 2,100 megawatts of electricity every day. Our capability has been recognized by our client, in which we have successfully completed a contract in 2005 to operate, maintain, and train the staff of the cogeneration plants owned by Petronas Gas Berhad, located in Gebeng and Kerteh, Terengganu, Malaysia. This has marked our first O&M operation for an external party. In 2013, TJSB was awarded a 5-year O&M contract by PT Mera Energy Indonesia to operate and maintain their 120 megawatt electricity and 55 ton per hour steam production coal-fired power plant located in Banten, West Java, Indonesia. Our power plant simulator is an effective training tool that gives the participants a real-world feel of conducting operations and dealing with potential emergency situations. A power plant's efficiency and availability is dependent on the performance of its operation and maintenance staff. TJSB's Training and Competency Services offers customized training modules to equip O&M staff with the fundamental knowledge and skills needed to ensure that the plant operates smoothly and efficiently. TJSB also offers plant technical audit support, technical due diligence consultancy, and implementation of proven O&M tools and methodologies to guide our clients to identify their operations' best practices and areas of improvement to maximize profit. This is what we are, this is what we do, and this is what we believe in. TJSB forges ahead to sustain our reputation for delivering world-class operations and maintenance service in the power and water industry. Teknik Janakuasa Sendirian Berhad, your preferred partner in maximizing values from power and water assets.
Ladies and gentlemen, so this is the end of our opening ceremony this morning. I will pass the floor to Professor Insinyur Dr. Zohana to chair first keynote sessions.
Thank you, Dr. Nick. So our first keynote speaker would be from Mr. John McDonald from GE Grid Solutions. So while John is preparing his slide, I would like to read his brief CV. Actually, he has a long CV, but I'll just read the most important one. John McDonald, PE, is a smart grid business development leader for GE's Grid Solution business, and he has 46 years of experience in the electric utility transmission and distribution industry. He received his BSEE and MSEE degrees from Purdue University and an MBA degree from University of California, Berkeley. He is a Life Fellow of IEEE member for 49 years, and was awarded the IEEE Millennium Medal, the IEEE PS Excellence in Power Distribution Engineering Award, the IEEE PS Substation Committee Distinguished Service Award, the IEEE PS Meritorious Service Award, and also the 2015 SIGRE Distinguished Member Award. John is past president of the IEEE PS, the VP for Technical Activities for the US National Committee of SIGRE, the past chair of the IEEE PS Substations Committee, and also the IEEE Division 7 past director. He was on the board of governors of the IEEE Standard Association as in an IEEE Foundation director-elect. John received the 2009 Outstanding Electrical and Computer Engineer Award from Purdue University, and he teaches a smart grid course at the Georgia Institute of Technology, a smart grid course for GE, and a smart grid courses for various IEEE PS local chapters as an IEEE PS distinguished lecturer. He has published 150 papers and articles and has co-authored 5 books and also 1 US patent. So the title of today's talk would be Grid Modernization, Technological Advancement Beyond Smart Grid. So John, I'll thank you again for, I think you are at like maybe 9 p.m. At night?
Yeah, it's about 8:30 p.m. on Sunday night.
Okay, so I'll pass the floor to you.
Okay. Thank you very much, Sahina. It's a great opportunity, and I really appreciate the invitation. We're very close friends through IEEE PES activities,
Yes,
and
indeed.
though we can't get together in person right now, we at least we can get together virtually.
Yes, true.
I'll share my screen, okay, and bring up
Okay.
my slides. Let's see. So let me do this again here.
Yeah, sure.
There we go. So I'll share again. Let's see. There we go. So Hannah, can you see the slide?
Yes, yes, you can.
And now I just put it in slideshow.
All right, that good.
And can you see it move?
Yes.
Okay.
Okay. So John, you also live to Facebook and YouTube.
So it's on with Facebook and YouTube?
Live, yes. Mm-hmm.
Okay.
All right. Okay, so
Very
it's all
good.
yours now. Yep.
All right. Well, thank you again. It's a real honor for me to give the first keynote here on the first day of the conference. And I've made a number of trips to Malaysia to teach courses as a IEEE Power and Energy Society distinguished lecturer. And I've been a distinguished lecturer since 1999, so over 20 years. And I typically do at least 12 or so each year. You know, for the past year, they've been virtual, but previous to that, it was traveling all over the world. As Zahana said, I was the IEEE Power and Energy Society president in 2006 and 7, and actually on the governing board of PES from 1998 through 2009. So for 12 years. Let me I'm very proud to say that this is my 50th year of IEEE membership. I'm an IEEE Life Fellow, but 50 years now active in IEEE. I joined as an undergraduate student, electrical engineering student at Purdue University. I've been working full-time 46 years in the electric utility industry, and married 41 years, have 2 children, 2 grandchildren, and I'm very proud to say too that I work out with a personal trainer. Been doing that for over 10 years and run 5K races and really try to, in addition to doing a lot of good work, I try to stay in very, very good physical shape. Okay, that allows me to travel internationally pre-COVID and hopefully as we get through COVID. Okay, so these are the topics. Now, with grid modernization, I don't want to repeat the things that we've been doing, but I want to focus on the things we need to do for the future. That's what I say, technological advancements beyond smart grid, beyond what we're doing today. And these are the key topics that I'm going to touch on through this talk, okay? So the first thing is key industry societal trends. And the question is, why do I start with this? Well, I really think it's important that all of us have a balance between what I call internal and external focus. Internal focus is that we go to work, we do our work, and we come home. And that's, if we have 100% internal focus, we're really just focused on our work. The question is, the decisions we make for our company, are they really the best decisions for our company? And why I say that is, do we really know what's happening in the world around us? Because we may be making decisions that we think are the best, but if we don't know what's happening in the world around us, they may not be the best, right? They may be suboptimal. We may decide to buy equipment from a vendor, And then 6 months later, a new industry standard is published, and it changes the communications protocol that the equipment should be using. And we just bought equipment that used a previous protocol that's no longer needed, no longer in demand in the industry. Our equipment could be obsolete, okay, because we didn't know what was happening in the world around us. So ideally, we want to balance between internal focus and external focus. And external focus would be what Zahina and I and many of you others are doing, is being involved in IEEE, being involved in CGRE, right? Being involved in IEC, helping to write the standards for the industry, you know, writing papers, presenting papers, being involved in panel sessions, going to conferences. This is how we learn what's happening in the world around us. So some of the key trends, you know, we've definitely transitioned from devices and systems to holistic solutions. Why? Well, a device, you know, with devices today are microprocessor based with two-way communications. And, you know, the IEEE term that we use for those is intelligent electronic device, IED. And an IED has internal processing capability, but also has two-way communications, which means that that device can be a node in a bigger network, okay? Same with a system. A system could be a system by itself, or it could be part of what we call a holistic solution. Holistic means company-wide, not just for the planning group, not just for the protection group, not just for the maintenance group, but company-wide, okay? We break down the silos of the individual groups and bring all the groups in the organization together. That's holistic. A solution is a set of technology components integrated together to successfully interoperate to meet the business needs of the customer, of the electric utility, let's say. So for a device, rather than a relay, let's think of a digitized substation with IEC 61850, right? Merging units, goose messaging for protection, process bus, things like that. Rather than a monitoring and diagnostics device on a transformer by itself, let's think of asset performance management, right? APM. Rather than a capacitor bank on a distribution feeder, let's think of volt-var optimization, okay? So, you know, those are holistic solutions, not just the device. And the reason is the holistic solution has much more benefits to the customer than the individual devices themselves. And because the devices have two-way communications, we can build this holistic solution. Now, success is not just technology, but it's industry standards and policy. All three are very, very important. Technology without standards, without compliance to standards, will not successfully interoperate, okay? We won't be able to take devices from different vendors, integrate them together and have them successfully interoperate without compliance to the same standard or the same set of standards. And policy is the strongest driver to incentivize a customer to buy the technology, right? Policy is extremely important. So, you know, we spend a lot of time with policy makers to try to shape policy. What's really important today is grid flexibility or self-healing, you know, to be able to reconfigure the grid. We have logic. I will show you a little later. We can put on, for instance, the distribution part of the grid where, you know, we can automatically detect the fault, locate the fault, isolate the fault, and restore service upstream and downstream of the faulted segment within 1 to 2 minutes. Truly a self-healing grid with no person involved, okay? But part of this is a cultural change in, one thing is the technology, and the other aspect is convincing the customer, convincing the people at the customer, right? The engineers, the people, to accept this new technology, have confidence in the logic, and be able to close the loop on the logic take the people out of the loop and let it self-heal. Now, the next is resiliency. What's very important is resiliency of the grid. I think, you know, as we look around the world on a continuous basis, we see so many extreme weather events around the world that are really putting a lot of stress on the electric grids, okay? And so we need to really think about how can we improve the resiliency of the grid. In fact, this is very important to customers. You know, we surveyed thousands of utility customers, and we said, how many of you would be willing to pay $10 or more extra per month on your electric bill if the extra money went to making the grid more resilient? And this was in the United States, and 41% of the customers on the eastern half of the United States said yes, and 34% on the western half of the United States. Reason for the difference is the customers on the eastern half of the United States have experienced many, many more outages than those in the west. So the value of resiliency is much greater to them, okay? But this is very important to customers. And so we see a lot of emphasis today on resiliency, so much so that it's driven much more focus on microgrids, taking one heterogeneous grid and dividing it up using strategic microgrids, so that a microgrid that has its own generation, and typically, you know, renewable generation, can be islanded and still continue to operate when the surrounding grid around it has a problem, okay? So it adds more strategic microgrids can add more resiliency to the total grid, and there's much more focus on that today. We'll talk a little bit about big data. I saw that one of the tracks with the conference is big data. A number of us spent a couple of years, and we wrote a new book just published in 2018 called Big Data Application in Power Systems, okay? Published by Elsevier. And I wrote the first chapter of the book, which is titled A Holistic Approach to Becoming a Data-Driven Utility. Two key points there. One is holistic approach, meaning company-wide, as I said before, and a data-driven utility. The decisions by the utility are based on data. That's why so many manufacturers and so many utilities are now hiring data scientists, right? More of the decisions are driven by data. More of the automation systems today have cloud components, okay? And then we see social media being used more by electric utilities. Instead of assuming that a customer will use a phone to call the utility with outage information, 70% of the customers prefer to interact with their utility through social media. So for instance, one way to do this would be, say, my utility, rather than having my phone number in my customer record, they have my Twitter handle, okay? And so when I have outage information or any communication with the utility, I send a tweet to the utility. They know from my Twitter handle my customer record, and can intelligently parse the words in my tweet to extract the outage information and put that in the outage management system, okay? We've been doing this for 6 or 7 years. This isn't new. And we're just, you know, emphasizing the increased use of social media by electric utilities for customer interaction. And then one thing that we'll emphasize here is to be able to truly have enterprise data management, to take valuable information from the operations side of the utility, what we call OT, operations technology, extract it, bring it across the firewalls of the secure operations network and over to the corporate side, the IT side. We need to have seamless interaction between the operations part of the utility and the IT part, OT and IT. We need convergence of IT and OT to support enterprise data management. And we can sum this up by saying, before we think about smart grid, we need to make sure we have a strong grid, right? Strong grid before smart grid. We need to make sure Our communications infrastructure is robust, can support the new applications we're thinking about with respect to smart grid. And we need to make sure IT and OT are truly converged to support our enterprise data management. That's the strong grid, communications infrastructure and enterprise data management. If that foundation isn't strong, we'll be buying new things, implementing those new things, and we won't get the performance that we expect because their underlying foundation has weak spots, okay? So don't invest, right, in new applications or new technology unless you're sure your foundation is strong and can support it. So, as I said, IT and OT convergence is very important. We improve the utilities' reliability, their operational performance, and the overall productivity of the workers. We increase energy efficiencies. We decrease carbon emissions, okay, help the environment. We're empowering consumers now to manage their energy use and save money without compromising their lifestyle. You know, we call this in-home enabling technology, okay? And we're also optimizing renewable energy integration so we can have broader penetration. So again, we want to bring together, we want to integrate the electrical and information infrastructures. This will deliver meaningful, measurable, and sustainable benefits to the utility, the consumer, the economy, and the environment. This really sums up what we want to do. And the best thing about smart grid is there's much more focus now on the distribution part of the grid. So those of us that have been involved in the industry for a long time, you know, I've been adding intelligence to grid with the companies I worked for over 46 years, 50 years with IEEE, and leading standards work with IEEE for over 35 years, primarily in the IEEE Power and Energy Society Substations Committee. I like to say it's a smarter grid, not so much smart grid, because many of us have been adding intelligence to the grid for a long time. So we've had a smart grid for a long time. The difference is what we're doing today is shaded in light green, okay? So I made this slide to say, let's differentiate what we've been doing in the past, which is gray, light gray, versus what we're doing new, which is in light green. So you can see voltage control here is half shaded. Well, we've been doing voltage control for a long time. You know, voltage is directly proportional to load. So, you know, one way to manage load, if the load is increasing, like on a hot summer day, and it's getting close to the previous peak, and we don't want to exceed the previous peak, we can lower the secondary voltage, which lowers the load. So why is it shaded halfway? Well, the gray part is what we've been doing in the past, but the light green part is the fact that we're integrating voltage control today with reactive power control. We call it integrated VOLVAR control or VOLVAR optimization, okay? Because we used to do VAR control by itself. There's significant benefits to both voltage control and VAR control. In fact, in the mid-1990s, I wrote a power factor control application for a SCADA vendor that I was working for. And a utility in the northeast of the United States implemented that on their existing SCADA system, and it saved them over $250,000 per year in losses. So very significant benefits. In fact, today with distribution, we say for every dollar the utility invests in distribution optimization, they're getting $5 to $6 back. Very strong benefit to cost ratio. We're also, you know, as I said, we're integrating renewable generation and increasing broader penetration. Now in the middle here, I shaded halfway sensors. You know, we've been adding sensors to the grid for a long time. The difference today is we have more specialized sensors that we're adding. For instance, this sensor that I show here, we would implement on a transformer, and the oil from the main tank of the transformer would go through this sensor, And this particular one can detect up to 2 gases dissolved in the oil of the main tank of the transformer, as well as a number of other health pieces of data. But I could increase that with other sensors and actually go up to detecting 9 different gases in the main tank of the transformer simultaneously. Okay, so we have a lot of capability today with very specialized sensors, and that's why utilities have really adopted what we call an observability strategy. You know, which means what data do I need from all the parts of my service area, and am I getting the data that I need? Am I getting it at the frequency I need it? Okay. Observability strategy, because what utilities find is they aren't getting all the data they need. When they buy let's look at the box to the right here, distribution management system, a DMS, or sometimes we say ADMS, advanced distribution management system. When a utility invests in a distribution management system or a SCADA system for distribution, right, to manage the increasing complexity of distribution, there's a lot of very important applications, which I'll go over in a minute, on that DMS. But remember now, those applications can only optimize what they know is happening on the grid. If we don't give those applications the data, all the data they need, they'll be limited in the benefits that they can provide the utility, right? So observability strategy is very important. We have to make sure we're getting all the data that we need, and we're populating or feeding it to all the applications that need that data to provide the most benefits to the utility. And then we have distribution automation here, which is downstream of the substation, feeder automation. We'll talk a little bit about smart meters and the additional data that they can provide to the utility. Okay. So first, let's see some examples here of smart grid holistic solutions. Again, holistic means company-wide, enterprise-wide. And remember, solution is set of technology components integrated together to successfully interoperate to meet the business needs of the utility. So this is examples of 6. On this slide, I'll introduce them. On the next slide, I'll show the technology roadmap in detail of what are the technology components associated with each of these, okay? So first is asset optimization. We started with critical transformers, okay? And then we went to high voltage and medium voltage circuit breakers. Second is demand optimization. This is aggregated load that we're using in the control center as part of generation control. So it may be more cost effective that when load increases and frequency drops, instead of ramping generating units to bring the system frequency where it should be with AGC, with automatic generation control, it may be more economic to pull the trigger on some aggregated load to lower the load. Okay, so we're using demand optimization today as a dispatch tool in the control center. And then we have smart meters and two-way communications. Distribution optimization today. As I look around the world, I see this is probably the strongest business case today, distribution optimization of any of the smart grid business cases. And in many places of the world, I would say asset optimization is probably number 2. There's more focus today on monitoring and diagnostics of critical assets, and then asset performance management and what we call asset lifecycle management, APM and ALM, by most utilities. We get into transmission optimization. A lot of the focus here today is on synchrophasers and getting more value from synchrophasers. You know, there's a lot of insight into the behavior of the grid when we can get 40 to 50 samples per second, right? As opposed to SCADA data, which is 2 to 4 seconds. It gives us much, much more insight into the operation of the grid, the behavior of the grid. And we want to use that more, take more advantage of that. And then lastly is workforce and engineering design optimization. As I look at countries around the world, we're all in different situations, but just an example in the United States is within the next 5 years, 40% of all the employees in the energy field, not just the engineers, but all the employees, 40% of the employees and 60% of the executives will retire. Okay, think about that. 40% of the employees and 60% of the executives will retire. Now, think about the work we do. A lot of the work we do, I call it an art as opposed to a science. If it was a science, we could read a book and be the best protection engineer in the world, right? But it's not that easy, right? What we do is an art. You have to read the book to know the basic science, but then you need to spend years with experienced engineers to develop the art, right? It doesn't come quickly. It takes time. And that's why every organization today should have formal mentoring programs to make sure that all of our young professionals have at least one mentor that they spend time with on a regular basis, okay? Because our experienced people will not work forever. And we don't want to lose that art aspect when they retire, okay? So let's take each of these 6 and look at them in a technology roadmap. So in the upper left here is the office and the control center. Lower left is substations. Middle and the low, these are the distribution feeders. And so if we look at the upper left, well, we don't have time to go over all 6 of these. Let's just pick one. Pick one holistic solution. Let's pick distribution, which is the light blue boxes. So you can see in the upper left, these top 4 blue boxes are software applications on a DMS. We have fault detection, isolation, restoration, integrated Volvar control, optimal feeder reconfiguration that we use in restoration, and distribution power analysis. This is our 3-phase load flow program, okay? Then here we have the distribution management system and the outage management system. Go down to the substation level, we have the station controller. We're showing applications at the substation level. And what we mean by that is we actually will take FDF, fault detection, isolation, restoration, and integrated Volvar control, and not only run these centrally on the DMS, but we also will distribute these down at the substation level. And we've been running these at the substation level also. Then on the feeders, we have switches and breakers, and we have Volvar devices. So these switches and breakers will support the logic of FDIR, right? We need to, when a fault occurs, we need to detect it, locate it, and isolate it. So we use these switches and breakers to isolate it. When we do Volvar control, we need capacitor banks, voltage regulator devices on the feeders, and that's these Volvar devices, okay? Now, why are industry standards important? All these blue boxes will not necessarily be from the same vendor, but they need to successfully interoperate. So, it's very important that they comply with the same standard or sets of standards. And I'm going to talk a little bit about standards a little later on, okay? And what we've done in the industry. But you can see that there's a lot of light blue boxes here that all need to successfully interoperate with each other. So one of the things that is important here, 2 things actually, is investing in 5 key components. And these key components are smart meters, number 1. Number 2 is the metering two-way communications, which we call AMI, automated metering infrastructure. 3 is the geographic information system. 4, the outage management system. And 5 is the DMS, okay? So not just invest in those and keep the functionality up to date, but the integration of those is extremely important. In fact, when a utility buys a DMS today, distribution management system, if the project is done correctly, only 30% of the total project cost is the cost of the DMS from the vendor. 70% of the total project cost is the cost to integrate that DMS with other systems and devices in the enterprise. And it's the integration and how well that's done that's a measure of the resiliency of that utility's grid. And what I mean by resiliency is when an extreme weather event occurs, how many outages are there, and what's the duration of those outages, okay? So, as I mentioned with smart meters, in addition to meter readings, we will ping certain smart meters to get the voltage and bring that and put that into the DMS network model. Why? When we do volt-var control, we need to make sure that the voltage at the customers at the end of the feeder are not below the minimum standard in our country, okay? In the United States, we have 120 plus or minus 5%. It's an ANSI standard, American National Standards Institute in the United States, C84.1, that says the voltage at the customer premise must be 120 plus or minus 5%. Must be. So we don't want to get near 114 volts, which is 120 minus 5%. And we want to know what that voltage is, particularly on long feeders with more voltage drop. So we can ping smart meters on those at the ends of those feeders to find the voltage. And then when the when there's an outage, the smart meter will have enough energy in it through a capacitor that's charged to make one last gasp communication to the outage management system to report the outage, okay? The geographic information system is the reference system for the network model information for the OMS and the DMS. We also take status changes from the DMS and bring those into the outage management system. The outage management system has a network model, and if it knows that a certain feeder breaker has tripped, because it has the network model, it knows all the customers connected to that feeder, and it knows now that all those customers have an outage. Okay, very important information. And then we talked about customers wanting to move from phone calls to social media. The preferences interact with your utility with social media. So I mentioned the increased emphasis on microgrids with resiliency and also distributed generation. So, we can connect renewables either at the transmission level, the distribution level, or at the end user level. What I'll talk about here is distribution and end user. The one challenge here is that what I say at the bottom of the slide here is the distribution controls and protection were traditionally we took advantage of and designed for assuming electricity was flowing in one direction. And, when we start integrating renewables, distributed generation on the distribution system and at the end user level, we have unique challenges in that we now have two-way power flow, and we'll also talk about voltage regulation concerns, okay? But now we have two-way electricity flow. If I'm a field worker, I go out to the field to do some repair, some maintenance. I used to be able to open the upstream device and have a safe work situation. That's not true anymore. I can open the upstream device and still have an energized line because of distributed generation that's integrated, further down on the feeder, okay? So it's a more challenging situation. So some of the industry challenges is we have open circuit over voltage due to unintentional islanding, right? We have protection ratings that may not match our fault currents. Why is that? Well, when we did our short circuit studies to determine our protection settings, we typically modeled the grid and really considered the source side contribution to the fault only. Okay. Now, as we integrate distributed generation, and as the penetration of distributed generation grows, we could have a significant contribution to the fault from the load side. which typically we didn't take into account when we did our short circuit studies to determine what the ratings should be of the protection equipment. Okay, but what's even more challenging is what I say next is there's varying fault currents due to the distributed generation. Okay, the sun isn't always shining all the time. The wind isn't always blowing all the time, right? So these fault currents can vary dramatically because of the intermittency of the distributed generation. This is even more complicated, okay? So as a protection engineer with a high penetration of distributed generation, how do we truly determine what the protection rating should be? Okay, and then we'll talk in a little bit about stress on voltage regulation equipment. So this is a microgrid installation, and it's a rural village in Canada that's not near any utility. So it's a village on its own, and there's industrial and residential load, and their base generation is diesel, which is pretty typical. But they have hydrogen fuel cells, they have PV panels for solar generation, and they have some low head hydro, okay? And there's industrial load and residential load. So what we did was we took a microprocessor-based relay and added logic to that to be the microgrid controller right here. And then these blue boxes here at every location are high-speed communications devices. So we know every second, we know what the load is, what the generation is, we know exactly the situation. And what the controller is doing is we want to make sure our load is satisfied all the time, but we want to minimize the use of the diesel generation and maximize the use of the hydrogen fuel cells, the solar generation, and the hydro generation. Okay, this is a typical microgrid. Used to be the microgrids, you know, the common installations in the beginning for microgrids were three things: military bases, university campuses, and rural villages. And then, as I said, with the increased emphasis on grid resiliency, we see much more focus on microgrids today, strategically by utilities in dividing up their heterogeneous grid into strategic microgrids. Now, this is an example of a real installation. This is in the United States, in Philadelphia. And this used to be an area where it was called the Navy, Philadelphia Navy Yard. This is where the United States Navy built and repaired large ships, okay? And when it was closed, it was turned into an economic development zone, Industrial Development Corporation, an economic development zone. And we implemented several microgrids there. And this is in combination with the independent system operator, which is PJM, the local utility, Philadelphia Electric Company, or PECO. And in addition, then, the U.S. Department of Energy was involved, and Penn State University from a research point of view. And with the several microgrids is a full distribution SCADA system that we added, a control center, and a network operations center. And each of the microgrids has an automation control system. And this, you may have heard of this software. This software was developed by one of the U.S. Department of Energy laboratories called Pacific Northwest National Lab, PNNL. And they developed its three-phase software. It can model the grid on a full three-phase basis through three-phase analysis, and it's free. It's open source, okay? There's training materials online, and the software is available for free. And this is, it's called GridLab-D, and this is what is used here at this site for three-phase analysis, okay? Now, as the penetration of renewables grows, how do we deal with the intermittency? Okay, what are some of the technology solutions? Of course, one is what we call bridging storage. How do we bridge the intermittency? Well, we can use energy storage, right? Lithium-ion batteries for quick, instantaneous frequency support. But the other thing is we can use new fast start thermal generation. This is typically natural gas fired, and it's not only fast starting, but it's fast responding, okay? And in fact, a couple of years ago, GE, we announced a new, what we call electronic hybrid gas turbine, which is an integrated system that has 10 megawatts of lithium-ion batteries and a 50 megawatt fast start, fast responding natural gas fired turbine generator with software that optimizes the operation of the two integrated together. So it's very nice because it can respond instantaneously with the lithium-ion batteries, but it can also then respond to a more needs with more of a long time duration with the turbine generator, and the turbine generator can recharge the batteries. Okay, so it's a very optimal operation of the two working together. So as time goes on, we'll see more and more technology solutions to help us with the deal with the intermittency, because the penetration of renewables will continue to grow, and so we need technology solutions to deal with that. Now, as the penetration of renewables grows, particularly at the consumer site, at the consumer level, and what I mean by that is rooftop solar PV panels, right? Homeowners putting photovoltaic panels on the roofs of their homes or businesses. What happens is that it creates tremendous volatility in system voltage and reactive power on the low voltage network. So companies have developed with low voltage power electronics what we call low voltage network dynamic grid edge controllers. And by dynamic, we mean continuous set point control. Okay, edge of grid transforming into microgrids. These are grid edge controllers. And the reason is the volatility, because of the intermittency of the sun, creates tremendous volatility on the low voltage network. And we need to mitigate that. We need to address that with these continuous set point controllers. And I want to talk about this a little bit more because this is real and it's growing, and we need to address this because it creates some problems on the grid. So I wrote an article in Power Electronics magazine over 7 years ago, and the reason it was Power Electronics magazine was I talked about the impact of high penetration of rooftop solar PV on the distribution system, and I talked about 3 new applications of power electronics. Okay. Now, one of my takeaways with this article was I really want power electronics researchers and at universities and power electronics experts in industry to start working more closely together with power system analysis researchers and industry experts. We have real needs of power electronics in the power system analysis today. And what I see at universities and what I see in industry is the power electronics experts really work unto themselves and the power system people unto themselves, and I don't see them coming together like we need. And that's why I wrote this article, and as I said, over 7.5, almost 8 years ago. The 3 applications I talked about in the article were the substation transformer online tap changer, right? The online tap changer in the substation. Well, we just talked about low voltage network dynamic grid edge controllers and increased capability from inverters. And the reason that I want to talk about the tap changers is in my article, I actually had voltage information from a feeder in San Diego, California, where on this feeder, over 35% of all the homeowners had rooftop solar panels. that penetration is really high. It's huge, over 35% on the same feeder. And these homes were along the Pacific Ocean. So in the morning, they had what we call a marine layer of fog from the humidity in the ocean, the water. And as the morning went on, the sun would eventually burn the fog away, and all of these homes began generating at the same time. You should see the voltage waveform on that feeder. You have over 35% of the homes on that feeder all beginning to generate at the same time. The voltage spiked, and then it oscillated. What happened, do you think, to the tap changer in the substation, right? A tap changer is a mechanical control device, 16 raised positions, 16 lower positions, and 1 neutral position, but it's mechanical. It operates more frequently when the primary voltage changes more often, right? Because its goal is to keep the secondary voltage constant. Well, with this volatility from the high penetration of renewables, the lifetime of this tap changer in this substation for this feeder went from a expected lifetime of over 35 years to less than 2 years. It was operating 5, 6, 7 times per day. Now it was operating over 120 times per day. Okay, so the continuing use of mechanical controllers on the grid as the penetration of renewables grows is just not feasible. And that's why, we and others have built prototypes of a power electronic based tap changer. Okay. And that's why we have these grid edge controllers. That's why we're talking about much smarter inverters with not only increased functionality, but greater external control capability. This is real. And as the penetration of renewables grows, we're going to see this more and more often. So impediments at the top, there's still a lot of challenges here with distributed generation. In many places of the world, we have a lot of wind, but we have a lack of transmission at the point to really harness that energy and couple it to the grid. But we have a lot of enablers, things that we've accomplished, better forecasting, as I mentioned, a better thermal fleet, natural gas-fired turbine generators, faster starting, faster responding, okay, things like that. But in any situation, and I'm just showing a few examples here with wind, if a utility is really thinking about this, you really want to model it and study it in detail and see what the impacts are going to be and really do a sensitivity analysis. These are just some of the studies our energy consulting group at G has done for different utilities in North America. And it's very, very important to really have a good feel for what the impact is going to be. Okay, so I mentioned a distribution management system, or I say advanced distribution management system. And, I said we're distributing some of these applications to the substation level. But this is the centralized model here where we have the ADMS, in the control center. And within the dash lines is the ADMS. Really has 2 parts, the basic SCADA platform, supervisory control and data acquisition, the basic functionality, but then all the high-powered applications here that optimize the distribution part of the grid, okay? And remember what I said is if we don't give these applications the data that they need, we won't get the full benefits of these applications. So on the right here is the substation and feeder devices. We need to make sure we have all the right data, fault indicator status, currents, voltages, coming in, right, to the ADMS. And then the applications analyze those, and then they optimize the grid, and the optimization is done through device control commands that are sent back out to the field. And as we said before, the geographic information system here is the reference system for the network model for the ADMS as well as the outage management system. So if we look at an ADMS, there's really 3 groups of applications on an ADMS. And let me just say that another fellow and I, we actually put together a 1-day IEEE PES tutorial just on advanced distribution management systems. We've taught it at many general meetings. We've taught it at many T&D conferences. When COVID, when COVID occurred about a year ago, the IEEE made our one-day tutorial free to any IEEE member. You know, they took some of the intellectual property they had and made it free so that people could take advantage of it at no cost while we weren't traveling and we were working from home. I don't know if it's still available for free, but it's 5 PowerPoint modules and it's a one-day tutorial that we typically teach. And it was recorded. One of the times we gave it, it was recorded, and that's what's made available. It's on the IEEE Resource Center. So this is the real-time DMS applications. This is what the operator uses in real time. These are the more analytical, on-demand applications. And I would really characterize this distribution power flow. Today, it's really both real-time and analytical application. Can be used for both. And then utilities will have a third group of applications called ancillary, which are kind of unique to that utility in terms of what other applications they want to include on their ADMS. Okay? Now, most utilities today, you know, their goal is to become a digitized utility, digitally enabled utility. But no utility can get there in one step. So one of the things that we want to work together with the utility and say, first of all, where are you today? Let's say the utility is at manual control and legacy methods, just as an example. And let's help put a roadmap together to go from where you are today to where you want to be, but in manageable steps. And by manageable, I mean given human resources and given financial, budget money, financial resources. But at every step of the way, there should be significant benefits to the utility. So let's say from a manual control and legacy methods, the next step would be adding remote control and monitoring or SCADA capability, customer status through trouble calls and smart meters, and circuit reclosers. Now we have 28% lower customer minutes interrupted compared to the base level. Okay, significant benefit. Now it's automation and visualization. We add distribution automation with a power flow analysis. We have network visualization tools and outage management prediction analysis. Now we have 43% lower customer minutes interrupted over the base level. Again, a significant step. And then we get to network optimization and utilization, asset performance management, and outage analytics, digitally enabled and much greater than 50% lower customer minutes interrupted. So what's important is what is the roadmap that makes sense to go from where we are to where we want to be in manageable steps. Another thing is making sure that every dollar we spend, the money we spend, we get the most benefits back. So here's an example of a utility, large utility with 856 distribution circuits that wants to improve their reliability, okay, of the distribution grid. Well, at first, the thought is, well, maybe we need to automate all 856 circuits. That'd be a tremendous expense. And do we really need to do that? Well, let's study this. And in studying it, we found that only 23% of all the circuits contribute 71% of the total outage minutes. So only 200 circuits account for almost three-fourths of all the outage minutes. So we focus on those 200 circuits first, automate those, and we're addressing almost three-fourths of all the outage minutes. Much, much better use of funding, right? And getting the most return for the money we spend. Now, to get more benefits from our investment, we need to really take a look at all these microprocessor-based devices, whether it's relays, whether it's monitoring and diagnostic equipment, whatever it is that we're implementing in the field. Because today a typical utility is getting no more, and I mean this, no more than 30% of the potential benefits from that investment of that $5,000 or $10,000 microprocessor-based device. And the reason is that we typically have only focused on the operational data from that device. That's the information that goes to the control center that the operators need to monitor and control the power system. Operational data. It's a time series of data at the scan rate of the SCADA master, and it's the real-time status, performance, and loading of the system. Fundamental information used by the operators, okay? But in 1984, when we saw the first microprocessor-based relay introduced to the industry, something new occurred. And that what was new was these new devices now had what I call non-operational data. And I wrote an article in IEEE Power and Energy magazine, the magazine for the Power and Energy Society, in 2003, that introduced these concepts for the first time in industry. Okay, now they're pretty much industry standards. I had done many, many projects, and I saw that utilities were not using this non-operational data. The primary user of this is someone other than the operators. Could be power quality, could be maintenance, could be asset management, but it's not the operators, okay? In fact, there's 25 to 30 business groups in the utility that need this data that's inside the microprocessor-based device. Example would be a digitized waveform from a relay. The I2T information for a circuit breaker in a relay. The operations counter in the relay for that circuit breaker. Dissolved gas, moisture content, and oil, in a monitoring and diagnostic device. Circuit breaker contact wear indicator like I2T. This is very important information. Asset performance management, maintenance, disturbance analysis, planning, power quality. And what I find is a lot of this data is sitting inside the microprocessor-based device, and it's not being extracted. And in many cases, because of the siloed operation of utilities, many of the groups don't even know that this data exists in a microprocessor-based device in the field within the utility. So this is a comparison of the two types of data. Operational is typically, as I said, time sequence is typically real time or near real time. It will use standard non-proprietary protocols to communicate this data, typically between the control center and the field. Non-op data is typically it's points or a file, mostly historical in time. And if it's a file, we may need to use a vendor-specific proprietary format to access it, which is very common today and very easy to do. So one of the exciting things today is the Internet of Things. It's truly the next productivity revolution. And we're connecting intelligent machines with big data and analytics and with people, no matter where the people are, any way we can connect at any time for intelligent operations. This is what we're doing. We're going to have more data available in a more timely fashion and much more powerful with respect to analytics and getting value from that data. This is what I mean by a holistic approach to being a data-driven utility. Data science, artificial intelligence, machine learning, the concept of the digital twin. This is all what we're talking about today in terms of the utility becoming the digitized grid, okay? Now, with big data, on the left here is the situation I find still at most utilities where every group in the utility is siloed. They have their own systems, their own microprocessor-based devices, and their own databases. And there's no sharing of information. On the right here is really the goal. And the goal is to break down the silos, have an IT infrastructure that's like a federated data mart, and truly have sharing of information. all the data, we look at all the data sources in the enterprise. We look at the data needs of all the users here, whether they're operational or non-operational, and we make sure that all those data needs are satisfied through the corporate network, through the IT infrastructure on the corporate network. This is what I mean by the strong grid. Communications infrastructure and IT infrastructure to truly support what we mean by smart grid or grid modernization. The goal then would be standard architectures, like this is a standard architecture in a substation with master data concentrator and slave data concentrator and the microprocessor-based devices, the intelligent electronic devices, where in light blue or cyan color here is all the data sources in the enterprise, and in green here is all the business, the stakeholder groups in the utility that now have all the data they need to provide the most benefits to the utility. Okay, and this is really the sum in one slide of what I'm talking about. We started with reactive on the journey to digital transformation, where we waited for something to fail, and then we reacted. Then we moved up to responsive, and I would say today we're at predictive, where we're trying to say what health information do I need from each of the assets, or what analytics do I need to predict a failure is occurring, to predict all the failure modes of that asset. But what's really cool about this is predictive is only halfway to where we could be. Okay, that's important. That's what's exciting about this. Next is prescriptive, and then autonomous. And this is truly much greater use of artificial intelligence, machine learning, and the digital twin. And again, if you're interested in this, I really recommend you get the book Power Big Data Application in Power Systems, because we're really focused on the future of big data, specifically for applications in power systems in that book. Okay? Now, standards are extremely important. I was part of a team that developed the Smart Grid Conceptual Reference Model, which is really 7 domains. If we think of smart grid going from turbine to toaster, from power plant to your home, and you think of that broad landscape, how would you draw that on one sheet of paper? Well, this is what we did. It's 7 domains, and these domains working with each other. Since 2017, we've updated this model. I was one of 11 smart grid experts chosen by the US government to help update this. And we published a Framework 4.0 document last year, which is free. It's a link on the NIST website. You can see NIST up here, National Institute of Standards and Technology. And we actually wrote what the US needs to do to be fully prepared for smart grid 10 to 15 years in the future, okay, which includes an updated version of this conceptual reference model. In addition, what we did was we looked through hundreds of industry standards, and we said we need to help the industry and narrow this down to a smaller group. And so these 16 standards here are what we call the Smart Grid Foundational Set of Standards. If you just focus on these 16, you've got all the significant standards you need for whatever you're doing in smart grid, whether it's generation, transmission, distribution, or the end use customer, whether it's cybersecurity, whether it's home automation, smart metering. These are all the key standards are here. And what's really nice, because I've been leading standards work for 35 years now, worldwide, from control center to control center, there's one standard accepted by the world, which is called Inter-Control Center Communications Protocol, ICCP. From control center to field, there's really just 2 standards. One is with North American suppliers, DNP3, which is IEEE standard 1815, or European suppliers will use 870-5 for serial communications and 104 for network. And then within the field, the worldwide standard is really IEC 61850, but in North America, we still use a lot of DNP3 in the substation and with feeder device automation. Okay, let me finish here with, after about 18 months of deploying smart grid projects, at GE, we stopped and we reflected back and said, what lessons have we learned and what changes will we make in the future? And
100%.
so, you know, an integrated, a holistic solution is a set of technology components, as I said. And the reality at the time was component technology wasn't as mature as was advertised when we combined all these components to create a smart grid solution. So remember, a chain is only as strong as its weakest link, okay? The maturity of a holistic solution is only as mature as its least mature technology component. So in many cases, we had to field re-engineer or upgrade technology components to meet objectives and expectations. So really look at every component in the smart grid solution. Also, we found how important standards were. When you take different vendors' components and you try to put them together and exchange information and talk to each other, you see how important compliance to the same set of standards is. Also, testing. Testing is extremely important. And not just testing in the laboratory or before you go out to the field, but end-to-end testing. You know, from the device in the substation all the way up to the control center or to the office. Very important. We also found that, you know, if you're a project manager here for a smart grid project at a utility, you have the responsibility for the project, but you also need multidiscipline authority. Responsibility and authority are two different things. You can have the responsibility to do the work, but if your manager hasn't given you authority, you won't be successful. And smart grid projects, you know, require the involvement of many groups in the utility, multidiscipline authority. We also found that project management was very critical. It's not just enough to have the best engineering team, but we found project managers were important. Consistent project management is very important. Project management guidelines. You want consistent project management with a program management office. And you need to have the very best, the A team, with not just technical members, but project management members. You could have the best technology in the world, the best engineering team in the world, and a project that's not successful because you had weak project management. Okay, project management is key. And then I'll finish up here with one of the things that we really weren't prepared for at the time was that we found with smart grid, we really have a new major stakeholder, and that's the end use customer. You know, up until that point, meter readers would read the meter, the utility would generate a bill, the customer would pay the bill, and there was really no engagement with the customers. Then when we wanted to put smart meters on the customers' homes or businesses, it was very important then to engage with the customers, manage their expectations. You know, what are the new services we can provide them with the smart meter? And we found that customer engagement was extremely important. And so residential commercial customers are a major stakeholder now, very important with respect to smart grid. So let me end there. And if there's time, I'd be happy to, I'll stop sharing. Let's see, go back to the screen here. And Zuhaina, I don't know how much time there is, but if there's any questions, I'd be happy to answer them.
Okay, thank you, John. So I think we have a few questions. Yeah, this is one question. Can you see the question?
Yes, I can.
Yeah.
That's a very good question. I think if you've read information on this, you'll find that, as you know, Texas is very unique, right? We have an eastern grid in the United States, a western grid, but Texas wanted their own grid, so they're not really coupled to the rest of the United States. They're independent. And that's a problem when you have what happened there recently, because you can't get support, right, from the rest of the United States. You're on your own. The other thing was in 2011, there was a similar problem with weather, and a report was written on what Texas needed to do to winterize their grid. And unfortunately, through politics, through a change in priorities, that winterization wasn't done. Okay, it wasn't done. People knew what needed to be done, but it wasn't done. And then you find that, the wind wasn't a problem. Even Texas has a lot of wind generation in the western part of the state, but that wasn't really the problem, even though many politicians said it was. That wasn't. One of the problems was you have a lot of natural gas-fired power plants, okay? But the electrical infrastructure to pump the natural gas, you need electricity to support the natural gas infrastructure. And if you don't have electricity, you can't get the gas to the plant, okay? Or if you have frozen gas pipes, you can't get the gas to the plant. So there was generation resources that weren't able to operate, and it wasn't because of wind, but it was because of just not winterizing the grid. So there were, they learned their lessons in 2011, but they didn't do anything. They didn't do enough about it. It happened again just now. Hopefully they don't, hopefully their priorities increase and they truly invest in the grid and winterize it. Okay. We have windmills operating in Antarctica. So windmills can operate in very, very cold weather. So it's not the cold weather. It's there were a number of factors other than wind that contributed to the problem.
So it means that history repeats itself after 10 years.
If you live long enough, like I have, you see history repeating itself. And if you didn't learn from it, Zuhaina, shame on you, right?
Yes, true.
We need to learn from history, right? Not ignore it. So
yeah, okay. I think we have another question. Let me see. Yeah, there's one question then.
Well, DC transmission has a lot of benefits, and now the thing with DC is the business case has to be strong enough, right? Because when you have converter stations at each end, that's significant cost. And so the length of a line has to be long enough to justify the cost of the converter stations at each end. A very short DC line is very hard to justify, okay? But in areas where you have synchronization problems, like when we bring in energy from Canada from the hydro resources in Canada to the United States, that's typically DC lines because of the synchronization between the Canadian grid and the US grid. So DC transmission, there's actually more potential applications of DC today than ever before. And one of what's driving it with smart grid is offshore and onshore wind. Okay, when we go to offshore wind, we have many windmills out in the ocean, and then we have a substation on a platform in the water, right? And then we typically use a underwater DC line to bring that energy to land, and then we have a substation on land, and then we go from DC to AC, right, to couple that AC energy to the grid on land. So we're seeing a lot more DC now being used on onshore and offshore wind, in addition to your typical applications as part of the grid, the interconnected grid. So we have a DC business that's very busy today because there's many applications of DC. There's tremendous growth now with onshore and offshore wind all over the world. Good question.
Okay. Yeah. John, I have one question. You've been working like more than 40 years, so you have seen, from the conventional system into this modern grid. So what are your suggestions for the new power engineers? What would be the new skills that they should have now?
I would say a couple things. One would be you really want to work hard on being a good problem solver. You know, when you're at the university, really work hard on knowing how to solve a problem, really knowing, taking all the information about the problem, thinking through it clearly, looking at all your options to solve it, and then knowing how to solve it, but working with a team of people. We don't do things by ourselves anymore. So you have to be able to know how to work with a team of people, get the input from everybody on the team, right? Take the best of that input. As a leader, bring the group to a consensus. The group can't do 15 things going forward, right? You have to bring to a consensus and then implement that, okay? The second thing would be is always think of the big picture. I talked about holistic solutions. I find too many young people just focused on the relay, just focused on the microprocessor-based device. Yeah, that has value, but it doesn't have the value that the holistic solution does. We need to help everybody always think of the big picture. At Georgia Tech, we have a systems engineering program which teaches students to think of the total system, right? Think of the big picture. And I would say the third thing would be everything is going to be driven by data. It's very, very important, truly, artificial intelligence, machine learning, the digitization of the grid, really knowing some about data science, and because that is the future. We're getting much more value now from data than we ever did before, but there's much more that we can do on that. Okay.
Okay, there's one more question. Maybe we can have it like, okay, there's one question there.
Yeah. During light load, if there's a lot of sunshine and we have a lot of generation during light load, you know, one thing is the utility could still purchase that energy and then maybe export it and sell it, or the homeowner could store that energy in their own energy storage equipment at home and use it for later on. So I would say the prosumer energy model would be a combination of how much do I want to sell to the utility during a light load period, and how much do I want to save myself? And a lot of that depends on the business model. In California, it used to be that if you consumed electricity, it was 10 cents a kilowatt hour. But if you sold it to the utility, they had to pay you 40 cents a kilowatt hour. So it's a very good business case. In fact, Zaina, we made an IEEE TV video on smart grid that's available on the IEEE TV website. I'm one of the speakers in it. And we went to the rooftop of a home in Southern California, and this person had just implemented solar panels on her roof. And he said, hey, I pay 10 cents when I buy electricity, but when I sell it, I get 40 cents. Okay. Which really shortened his payback period. That's a big spread. Okay. So this is what the prosumer energy model would be, a combination of, you know, how much would the utility be willing to buy? What would they be willing to pay for it? If it's a good business case like that, I would tend to sell it and make more money. And the utility, even though they may not need it at the time, they may have energy storage, or they may be able to sell it across the country to utilities that have a need for electricity at the time. Or if it's not advantageous, I may just store it myself in my own like Tesla Powerwall at home and use it for later on. So.
All right, thank you, John. Maybe one final question from me. So in terms of towards digital utility, what do you say? I mean, what are the state in your country now? Have you reached like 100% of the goal, or is it still something to go away?
We haven't reached 100%, and that's why that one slide, Zahana, I said it's the journey the
Yes.
journey to digital transformation.
Mm-hmm.
People asked me when I was leading the smart grid work, the smart grid standards work in the United States, John, when will all the standards be finished? And I said, they will never all be finished. It's a journey. It's not a destination, but it's a journey.
Okay.
And really, the journey to digital transformation, the more we go along the journey, the more we learn.
Yes.
And the more we learn, the more we see we can do.
Mm-hmm.
So I don't really see where we'll ever have an endpoint. You know, we'll always be learning. There's always more things we can do, and always more value that we can receive. Okay, but I showed 5 steps in the journey, and those are the 5 steps we work on today. And I would say there's some utilities in the United States that are much further along. And one of them in particular, New York Power Authority, their CEO, Gil Quinones, is very active in the industry giving talks. And if you want to research and find a good example of a utility that is far along in digitization, it's NYPA, the New York Power Authority. And there's a lot of talks and a lot of information from his involvement in industry conferences and meetings, where he's very he's very external, and he talks a lot about their journey and what they've accomplished. So I would say it's one thing to talk about it, it's another thing to do it, and they're actually doing it. It's a good example. So I would say, we have to be real. We say it's a journey, and if we do it right, we want to learn every step of the way. So we really never have an endpoint, right?
Okay.
There's always something more that we can do, and that's why I haven't retired yet. I'm 69 years old, and I'm 69, and I'm having more fun now, Zahina, than I've ever had. 50 years in IEEE, and I have no end point in time.
That's good, John. I'm really inspired by your achievement. So thank you, John. It's very educational talk, especially for me. At least we know now what kind of interdisciplinary thing that now include in power grid, right? And we're still going towards it. As you said, it's a journey, not a destination. So with that, I think we have reached the end of the session. I'll pass back to the before that, as a token of appreciation, we like to provide with this memento. I'm sorry we cannot hand it to you personally, but I hope that this would be sufficient to show our gratitude to you for having, to be here with us today. Thank you, John.
Well, thank you very much again for the opportunity. I know this is the beginning of the conference, and I wish you a very successful conference for the rest of today and tomorrow also. Okay.
Thank you. I'll post this to you also by email.
Okay. All right.
Thank you, John. So I'll pass back to moderator for this morning, Dr. Nick.
Thank you, Professor Insinyur Dr. Zohaina. We begin technical session at 11 a.m. Please make sure you are in the right virtual room. Thank you.